Welcome to Control Systems N6. Today's presentation is going to be on body diagrams, or if you prefer, body plots. And this is a module that needs a lot of explanations. And so I will advise you to watch this presentation more than once, just to make sure that you understand everything in details. Let's begin. First of all, what is a body diagram? It is basically just a frequency response technique of analysis. So basically what we do is that we will plot a gain function and we will also plot a phase function based on a transfer function that is given to us. And then we will study how those change with respect to the frequency. Okay, so you will have a transfer function that will be given to you like that. And as you can see, this transfer function is already in the frequency domain. And what you see here, omega, is actually the frequency. And so the transfer function is going to be a function of the frequency. And based on that transfer function, we will be able to plot a gain function and a phase function and study how those two change with respect to the frequency. Okay, and if you look carefully at this transfer function, you will see that it's one of an open loop. Okay, so it's an open loop transfer function in which you have two gains, okay, G and H, and you may get a question where those gains are given as a function of S, and so you will have to first bring them to the frequency domain, and then once you have the transfer function in the frequency domain, you can then go ahead and plot the gain function and also the phase function. Very important. And so plotting the body diagram is done on a graph paper, and this is the graph paper that you will use to plot your body diagram, and it is referred to as the 3-cycle semi-logarithmic graph paper. Okay, so this is a term that you need to be familiar with, because very often in your questions they will tell you to plot everything on a 3-cycle semi-logarithmic graph paper, which of course is going to be provided to you in your exam. And so you need to know that this is what they are referring to. It's this graph paper here. It's a logarithmic graph paper. Okay, very, very important. And so on the x-axis, you will have the frequency. So values for the frequency will be read on the x-axis, or should I say at the bottom here. That is where you will read the frequency. And the unit for the frequency, of course, is radians per second. And then here, what you will read will be the gain. And the gain is in decibels, okay? So the various gains will be pretty much written on this side of the graph. And on that side of the graph, you will write the phases, and phases are in degrees, okay? So this is what you will use pretty much for your body plots, okay? It's this 3-cycle semi-logarithmic graph paper. And it's important for you to understand that the frequency values are written at the bottom here, the gain values are written here, and then the phases are written there. The unit for frequency is radians per second, that for gains is decibels, and that for phases is degrees. Very, very important. And so what are body diagrams used for? Okay, pretty much they are used for the sake of determining the stability of a control system. Okay, so it's very important using it's very easy using body diagrams to be able to predict the behavior of a control system, especially as far as the stability of that system is concerned. Okay, very important. And so now I want to show you how you convert a transfer function from the Laplace domain to the frequency domain. In other words, how you go from the S domain to the omega domain, okay? frequency is omega. And so let's say you have a transfer function that is given to you like that. And by the way, in this module, whenever you see G multiplied by H, okay, capital G multiplied by capital H, okay, when you see those two functions multiplied, this is what the transfer function is equal to. Okay, so what I wrote here is actually a transfer function. However, in this case, it is still in the Laplace domain. So we need to go to the frequency domain. So how do we do that? It's actually simple. All you have to do is to substitute S by J omega, sorry, it's not W. Okay, some people think this is W, it's omega. It is, though it looks like W, but it's actually the Greek letter omega, and it stands for frequency. And so in order for you to move from the Laplace domain to the frequency domain, all you need to do is to substitute S by J omega. And this J here is actually the equivalent of I when you're dealing with complex numbers, okay? It's only that in control systems, we use the letter J, but it is actually the imaginary unit, okay? Very important. And so if we replace S by J omega, then GS become G of J omega, and H is also H of J omega, not HS anymore. And then here, if you replace S by J omega, on top you will have J omega plus 1. Here it's going to be J omega squared, and here it's going to be J omega minus 1, okay? So, and then this here, you can simplify it further if you remember that J is the imaginary unit, okay? It's the equivalent to I when you did complex numbers in maths, okay? And you knew that I squared was equal to minus 1. So J squared is equal to minus 1, or if you want, you can say J is equal to the square root of minus 1. And so once you remember that, then you can see here J omega squared is going to be J squared omega squared. So J squared is minus 1. So all this here is just minus omega squared. Okay, so you can simplify it further and you will write your transfer function like that. Okay, you see here J squared became minus 1, so we took that minus sign, and this is what you have here, and you go a step further to write it nicely, and this is what you will obtain for your transfer function. But now this transfer function, as you can see, is a function of frequency, okay? So it is in the frequency domain, okay? So it was given in the Laplace domain. Substituting S by J omega gave us the function in the frequency domain. So this is how you do it. So generally in your questions, they will give you a transfer function in the frequency, in the Laplace domain. And so you're gonna have to transpose it to the frequency domain, okay? Very, very important to know how to do that. And it's quite simple because all you do is replace S by J omega. And so let us speak about the gain plot and phase plot functions. First, let us talk about the magnitude of a transfer function. And here I will need to say that if you understand very well complex numbers in your maths course and you know how to change a complex number to its polar form, then what I'm going to explain to you here is really just a revision for you. Because in order for us to find the magnitude of a transfer function, we will use pretty much the knowledge that we have from maths when we're trying to find the magnitude of a complex number. Okay, and so if you remember how to convert a complex number to its polar form, what we did was find the magnitude of that complex number and find also the argument. Okay, so these are the things that I'm going to speak about here. So if you know how to do that, my explanation here is just going to be a deja vu for you. Okay, so in this case, the first thing I'm gonna speak about is how to find the magnitude of a transfer function. And so let's say you have a transfer function that is given to you like this, okay, on the screen. Remember I told you when you have the function g multiplied by the function h, you need to understand that you're dealing with a transfer function, okay? And so when you have a transfer function that is given to you like that, and you have to find the magnitude of this transfer function, well, what do you do? First of all, in this module, the magnitude is referred to as A, okay, capital A. And so capital A is the magnitude. And so to find the magnitude of this transfer function, you will remember from maths that when we're trying to find the magnitude of a complex number, we put these bars to say magnitude, okay? And so capital A is the magnitude, okay? So A will therefore be equal to the magnitude of this transfer function, or if you want, we can write it like that, okay? So it's the magnitude of all of this. And so if you remember your maths course when you did magnitudes, okay, the magnitude of a ratio is equal to the ratio of magnitudes. So that can also be written like that. And so we can find the magnitude of the numerator and divide that by the magnitude of the denominator. And now, if you have a complex number a plus bi, to find the magnitude of that complex number will be the square root of a squared plus b squared, okay? So you should remember that from your maths course. And so if we have to find the magnitude of this here, numerator and denominator, what we will get is this. It's going to be the square root of this squared plus that squared divided by the magnitude of this, which is the square root of this squared plus that squared, okay? So this is how you find the magnitude of complex numbers. And so this here will therefore be equal to that if you just work it out. And so that is pretty much the magnitude of this transfer function. And so once you have the magnitude of a transfer function, that allows you to get the gain plot function. And the gain plot function, we refer to it as gain A, okay, gain of A, and it is equal to 20 multiplied by the log of A, okay? And in this case, A is the magnitude of the transfer function, which is this. And so if we want to find the gain plot function, we need to do gain A, which is equal to 20 multiplied by the log of A being the magnitude of the transfer function, which is this. So if we do that in this case, of course, the unit for that is decibels, okay, as I showed you earlier that the gain is in decibels. And so if we do that here, okay, we apply this to find the gain plot function, which is gain A, then this is what we will get, okay? So gain A will be equal to 20 multiplied by log of that. If you look here, you will see that the square root sign, I changed it to an exponent, and you know that that is half. And so this to the power of half, and that also to the power of half. And you could simplify this further if you wanted to, but here my goal was just to show you how you actually get the gain plot function. And this is the function that you will use to actually plot your gains, okay? As you can see, this is a function of omega. So for omega is equal to 1, you will replace omega by 1 and find the value of the gain. And you can do that for many different points, and that will allow you to plot the gain function, okay? Very, very important. And so this is how you get it. So the gain plot function is gain of A, okay, and it is equal to 20 multiplied by the log of the magnitude of the transfer function. And its unit, of course, is decibels. Now, let us talk about the argument of a transfer function. Now, again, we have the same transfer function that we had here. Now we want to find the argument of this transfer function. Notice that this is just the same thing as finding the argument of this complex number that you see there, okay? And so we write it like that, argument of the transfer function, okay, arg, and you put in bracket this because that's the transfer function. And so argument of the transfer function will be equal